Okay, so today's lecture is Chapter 5, the second lecture of Chapter 5. So, let's go to page 36. Okay, so today we will start with contingency table. So contingency table is, let's start with the example. So contingency table looks like this. It is a good example of a contingency table. So in this table, we consider that the relationship between the tuition of business school and salary after the students graduate this business school. And so we divide the 67 top tier graduate students by three groups of low tuition group, medium tuition group, and high tuition group. And at the same time, so this we analyze the 5-year net salary gains for the MBA degree students, and we classify this 67 graduate schools so people as these three groups. One is small salary and medium salary and large salary. So small salary means that 50K per year, and medium salary is 50K to 100K per year, and large salary is more than 100K per year. So then we would like to see that whether is there the relationship between tuition and salary gain. So after this we make a table based on this investigation, and we find that 16 schools are low tuition, 19 is medium, and 32 is high. And 17 is, so we have the 17 small salary and 33 medium salary and 17 large salary, and we have 67 total number of samples. Okay. And the guys who has paid the low tuition and have a job having low salary is 5. Low tuition, graduate low tuition business school and have a medium salary is 10. Graduate low tuition and get a high salary job is, the number of this case is 1. Okay, something like that. And so in the other case, the case that somebody take the medium tuition business school, graduate the medium tuition business school and get a job with small salary, medium salary, and large salary is that 7 people, 11 and 1. And high tuition, graduate high tuition business school and have a low salary, medium salary, and large salary is 5, 12, 15. So that if we see this table, then we can so clearly see that the tuition and the salary. So, and our question is that are large salary gains more likely for the graduate of high tuition MBA program? So that is the question. Okay. So using this table, we can see the marginal probabilities. So marginal probability is that frequency that found by the dividing a row or column total by the total sample size. Okay, so for example, the probability of S2 means that medium salary gain. So probability of medium salary gain is, so we have 33 samples which has the medium salary, so 10, 11, 12. 33 cases are included in the medium salary, and we have all the number of sample is 67. So probability that business school graduated students has the medium salary is 33 divided by 67 and 0.4925. So in other words, 49% of the top tier school has a salary between 50K to 100K. On the other hand, so we can find another marginal probability. In this case, we will see this one. So, for example, the tuition, if we randomly selected people is graduated on the low tuition university is 16. Okay? So the probability that we randomly selected person is included in this T1 is that 16 divided by 67, so 0.2388. It is marginal probability of T1. So and okay, again, so using the same method, we can obtain the probability of S1 as here 17 over 67, and probability of S3 is here, so 17 over 67. Okay, and the same way we can calculate probability of medium tuition is here 19 over 67, and probability of high tuition is here 32 over 67. So that is the marginal probability obtained by the contingency table. Joint probability is that, for example, if somebody wants to know that the probability of event that the school has low tuition and has large salary gains. So we would like to know that intersection between T1 and S3. So we would like to know that probability T1 intersection S3. In this case, T1 intersection S3. So then we have this guy. So then probability that T1 intersection S3 is 1 over 67. Okay. So using the contingency table, we can easily calculate this intersection probability. So then using the same way, we can calculate other things. Probability that, for example, T2 intersection S1 is that T2 intersection S1 is this guy. So we have 7 over 67. And so on. So probability that T3 intersection S3 is T3 intersection S3 is this one. So 15 divided by 67 and so on. So we can calculate the joint probability very easily using this contingency table. So finally, we can calculate the conditional probabilities using this contingency table easily. So for example, suppose that we know that the school's MBA tuition is high, T3. Under this condition, we would like to know that the probability of event that salary gain are small, S1. So then what we would like to know is the probability that S1 given the information T3. So then it is probability that S1 intersection T3 divided by probability of T3. So then it is S1 intersection T3 and S1 intersection is 5. So then 5 over 67 over, so probability of T3 is the marginal probability 32, 32 over 67, and finally we have 5 over 32. So simply we see the contingency table, then conditional probability can be obtained by this row. So based on the T3, we would like to calculate the probability of S1 given T3, then it is 5 over 32. Simply here, we see that probability that S1 over T3 is 5 over 32, and finally we have this value. So using the contingency table, we can easily calculate this conditional probability. Here is another case. So probability S1 over T1 is, let's go to the table. And probability that S1 given T1 is here. So it is 5 over 16. 5 over 16. That is S1 given T1. And S2 given T2 is 10 over 16. S3 is given T1 is 1 over 16, and so on. So T1, probability of T1 is 16 over 67, and probability of S1 intersection T1 is 5 over 67. So probability of S1 over T1 is 16 over 67 divided by 5 over 67. So finally, 5, 16. So again, it is 5 over 67 given 16 over 67. So we finally obtain the 5 over 16. So everything is the same. And in T3 case is the same. Okay. So using this contingency table, we can very easily calculate the conditional probability. After we study the conditional probability, we can check the independentness. So for example, if the large salary gain were independent of the low salary gain, then the conditional probability, if they are S3 and T1 are independent, then probability S3 over T1 is the same as probability of S3. So let's check that conditional probability S3 given T1, then it is 1 over 16. And probability of S3 is 17 over 67. So these two value is not same. Okay? So the conclusion is that large salary gain are not independent of the low tuition. So they have some relationship. So we can conclude this one using this contingency table. So on the other hand, we can check the independentness using this fact. If S3 and T1 are independent, then please check the independent section. Then probability that S3 intersection T1 should have the same value as probability that S3 times probability that ST1. So this equation. So let's check this property again. So S3 times T1 is 17 over 67 and 16 over 67, and we have 0.0606. And on the other hand, the probability that S3 intersection T1 is 1 over 16. So let's see the S3 T1. So then we have 1. So 1 over 67. Okay. So therefore, this two value is not same. So we do not have this equation. So this equation is not satisfied. That means they are not independent. So the large salary gain are not independent of low tuition. Okay. So using the contingency table, so we can check the conditional probability and the independentness and so on. So please read this slide again carefully, and then please study the contingency table and conditional probability and independentness. Okay. And the next topic is tree diagram, but it is not so. Yeah, it is interesting, but so not important in this course. I will pass it. Okay, so Bayes theorem is very important, so I would like to concentrate the Bayes theorem. So Bayes theorem has many applications, but the Bayes theorem is given by this equation. Conditional probability of B given A, probability B given A is the same as probability that A given B times probability of B divided by probability of A. So using the Bayes theorem, we can change the probability of B given A to using probability of A given B. So BA, AB. So this probability of B given A can be obtained by the probability of A given B times probability of B divided by probability of A. That is Bayes theorem. Actually, probability of A is probability of A intersection B and plus probability that A intersection B prime, because here is A, here is B, then this part is probability that A intersection B prime, and this part is probability, not probability, it is A intersection B, and this part is A intersection B, and this part is A intersection B prime, and this part and this part are mutually disjoint, and union of them is again probability of A. So probability of A can be decomposed by probability of A intersection B, this part, and probability of A intersection B prime, this part. So then probability of A intersection B is again probability that A given B times probability of B, And probability of A intersection B prime is the probability that A given B prime times probability of B prime. So please check the definition of conditional probability. So we can change the probability of A to this sum of these two terms, this term and this term. So we have this equation. So that is general Bayes theorem, Bayes rule. So we will use this Bayes rule and find many interesting information. For example, suppose that 10% of women who purchase OTC pregnancy testing kits are actually pregnant. And that means that 90% are not pregnant. So, and this pregnancy testing kit has this information. If a woman is pregnant, then the test will yield a positive result 96% and have the negative result 4%. It is false negative. And if she is not pregnant, then the test will yield the positive result 5%. It is failed to positive. And a negative result 95%. So then, if somebody has obtained the positive result, then what is the probability that she is really pregnant? So that is the question. Okay? Let's see the problem carefully again. So, for example, if there is 1,000 women, so suppose that 1,000 women bought testing kits, then maybe 10%, 100, will be actually pregnant, and 900 may not. Okay, so then if we apply this 100 women this testing kit, then this test may give the answer that 4% has false negative and 5% has false positive. Okay, so then 4% of 100 pregnant women has false negative, and 5% of non-pregnant women may have the false positive. So 4 of them has false negative, and 45 of them has the false positive. Okay. So then, therefore, 141 women who will test the positive, and 96 will actually be pregnant. So the probability that pregnant given positive test is 96 over 141, so 68.909%. So let's repeat this explanation again using the table. So suppose that 1,000 women bought the testing kit. Maybe 100 of them are pregnant, and 900 are not pregnant, and all of them do the testing. So then, if this woman is pregnant, then 96% of these women may have the positive result. And 4% of this pregnant woman has negative result. So it is fail the test. And 900 non-pregnant women take the test. Then 5% of them may have positive test. It is wrong, but anyway, so because of this testing kit is not perfect, so 5% of them may have the positive test, and 95% of them has the negative test. It is correct. So it is an error, but it is possible. So let's draw the contingency table. So here is pregnant and not pregnant, and here is positive test and negative test. So pregnant and positive is 96. Pregnant but negative is 4. Non-pregnant but positive is 45. Not pregnant but negative is 855. So, and the sum of them is 141, sum of them is 859, and sum of these two value is 100, sum of these two value is 900. So then we obtain very good contingency table. Okay. Based on the table, so we would like to calculate probability that pregnant given positive test. So this one. So then we have to check that positive and pregnant, this one, positive and pregnant, divide by positive test. So 96 divided by 141. So then that is the conditional probability that the woman is pregnant given positive test. So that is 68.909%. Okay? So that is the answer. So if we use the Bayes rule, Bayes theorem, then we can solve this problem more simply. So based on the Bayes theorem, let's define the event. A is the woman has the positive result. A prime is that the woman who tests this testing kit has negative result. And B, event B is the woman is really pregnant, and B prime is not pregnant. So then, based on this information, so if the woman is pregnant, then the positive result has probability 96. So then probability that positive result given pregnant is 96%. And probability that negative result given pregnant information is 4%. And here, based on this sentence, we can obtain the probability that positive result given this woman is not pregnant is 5%, and probability that this woman has negative result given she is not pregnant is 95%. Okay, let's go back to that page. So probability that positive test given pregnant is 96. So if this woman is pregnant and do the test, then the probability that she has the positive result is 96. So if she, under the information that she is the pregnant and she may have the negative result is 4%. And probability that not pregnant, given information she is not pregnant, the positive result probability is 5%, and vice versa. So then, we suppose that 10% of women who purchase the OTC pregnancy testing kit are actually pregnant. So based on this information, we have that probability of pregnant is 10%, probability of not pregnant is 90%. Okay? So then we all have this information. And apply the Bayes rule, probability of B given A. We would like to know that probability of B given A. So we have the positive result under the information that she has the positive result. What is the probability that she is really pregnant? So that is the question. So we have to know that probability that B given A. But we know that probability A given B, and we know that probability that A given B prime, and probability of B and probability of B prime. So then using this equation, put the values into this equation, we have, so probability that A given B is 96%, probability of A given B prime is 5%, so 96, 5%, and probability of B is 10%, probability of B prime is 90%, here is 10%, and we obtain this result. So 68.9% chance that a woman is pregnant given that the test is positive. Okay? So we've studied the Bayes rule using two ways. One is intuitive approach, and the other is Bayes rule. Okay. So if we do not apply the Bayes rule, then there is only 10%, we only have the 10% probability for the pregnant probability. But if this woman has the positive result, then the probability that she may have the pregnant is 68%. Okay, so it is increased. So this positive result change the probability of pregnant to be high. Okay? But still we have around 32% of so non-pregnant. So it is not so perfectly correct. Okay? So the Bayes rule is that using the Bayes rule, we can obtain the probability of B given A using the probability A given B and A given B prime. So that is the point of Bayes rule. Okay, so that is the end of this chapter 5. So in the exam, I may ask you one question using the Bayes theorem. So please study this example carefully again. So and then you can solve the problem. Okay, that's it. Thank you.